Hello again, physics friends. Today we're going to talk about the center of mass and how we can use the center of mass as a proxy for an entire system, even if that system consists of an infinite number of particles. In particular, what we're going to show is that we can talk about the momentum of a system and its time derivative, or equivalently, we can talk about the mass of the system collectively and the position of the center of mass and its time derivatives. In other words, the momentum would be the mass of the system times the velocity of the center of mass, and the rate of change of that momentum would be the mass of the system times the acceleration of the center of mass. And because we know already that P dot for the system is equal to the net external force on the system, Newton's second law, what this equation here tells us is that we can treat the center of mass of our system as a kind of fictitious particle, an imaginary particle that moves in accordance to Newton's second law. So you can think of the center of mass as having an acceleration, and that acceleration is representative of the full system. Okay, well, let's start by looking at a kind of simple case where we have two particles. Okay, so here I've drawn two particles, mass 1 and mass 2, at two different locations, position vectors r1 and r2, and these two masses are in motion with v1 and v2. Okay. We can talk about the momentum of the system as being the sum of the momenta of each individual particles. So P system is equal to P1 plus P2. We also know that the individual momenta P1 and P2 are given by the mass of each object multiplied by its velocity. And this gives us a little bit of a hint because this quantity has a similar form to the numerator of the center of mass expression. So let's take a little mathematical aside and pause and remind ourselves what the center of mass, how it's defined. So our center of mass, RCM, is kind of like a weighted average of the positions, and the weights are the masses. So we have M1R1 plus M2R2 divided by the total mass M1 plus M2. Now, you can show that the center of mass of a system of two particles has to lie on a line that connects those two particles. And I'll indicate the center of mass with this green symbol. Okay. And when we say our center of mass, capital RCM, what we mean is the position vector, RCM, from the origin out to that point. Even though they're not necessarily an object at that location, the center of mass represents the system. So when I say this M1V1 plus M2V2 looks similar in structure to the center of mass numerator, that's just what I mean. We have a product of masses and vectors. In this case, it's a position vector, but we know how to convert a position vector into a velocity vector. We're going to take a time derivative. So let's do that. If we take the time derivative of the position of the center of mass equation, we get M1v1 plus M2v2 divided by the total mass. So we can rearrange this equation to find an expression that relates the total momentum to the total mass of the system and the velocity of the center of mass. We can take this one step further just to represent quantities as velocities instead of time derivatives of positions, right? So we could say M1v1 plus M2v2 is the total mass, M system, multiplied by the velocity of the center of mass. So let's take this expression and make use of it down here. And when we do that, we find that the total system momentum is simply the total mass of that system multiplied by the velocity of the center of mass of the system. Okay. So this is nice. It says, okay, you might have a collection of particles. Maybe it's two, maybe it's an infinite number of particles. And it's hard to keep track of all of those things. The motion might look fairly hard to understand. However, that entire complicated system can be reduced to a single object called the center of mass object, and you can just keep track of where the center of mass is. And that will tell you about the momentum of the whole system, number one. And number two, we know from Newton's second law that if you take the time derivative of the momentum of the system, that's going to be equal to the net force exerted on the system by external forces. That's Newton's second law. So let's take this a step further. Let's generalize, instead of for two masses, let's think about an arbitrary number of masses, say n masses. In that case, our system momentum will be the sum of the momenta of each particle from 1, 2, 3, all the way up to n, which we can write as a summation. The system mass will be the sum of all of the individual masses of all the particles, which we can also write as a sum. And then the position of the center of mass will also have an extended, so that be extended to be a sum from 1 to n. So the numerator will be a sum. The denominator, notice, is mcis, the total mass of the system. And let's give these three equations names, A, B, and C. We can start by taking equation C and taking its time derivative. So we have the velocity of the center mass. We can then recognize that the denominator is the total mass of the system. That is by equation B. So we can leave the numerator alone, and the denominator then becomes the mass of the system. And we can recognize that the numerator is the total momentum of the system. That's by equation A. So what we've discovered is that indeed the total system momentum is equal to the mass of the system times the velocity of the center of mass, r dot, for the center of mass. And this now is true for an arbitrary number of particles. So for me, there's basically two takeaways here. Number one, the momentum of the system can be written in terms of the total mass of the system times the velocity of the center of mass. Okay, so in some sense, you can represent the full system by a single point at the location of the center of mass, and imagine that the mass of that point particle is the mass of the whole system. And number two, because we've already shown that Newton's second law applies for the system, we can say P system dot dp dt for the whole system is equal to the net external force on the system. Okay. What that means is we can take a time derivative of the equation we just derived. If we do a time derivative of that equation, assuming the mass is constant, okay, by Newton's second law, that has to also equal the net external force. So what this is saying is, if you have a system and you apply an external force to that system, then the center of mass of that system will accelerate. And the acceleration can be calculated based on this equation. So here is a demonstration of how the center of mass can be used to characterize a more complicated system. So when this guy throws the tennis racket through the air, it doesn't look like a ball going through the air. There's a lot of fairly complicated motion. And we follow up that slow-mo video by tracking just the end of the handle. And as it's going, you can see it follows a fairly complicated trajectory, definitely not a parabola. Okay. But down here, we're claiming that the external force of gravity should accelerate the center of mass in the same way that it would accelerate a ball or another point particle. And indeed, if you track the center of mass of that racket, it follows this beautiful parabolic trajectory. And what's even more fascinating is if you follow along with the center of mass, then the rest of the racket is just moving in a circle around that center of mass. How beautiful is that? So thinking in terms of the center of mass can really simplify a system that looks otherwise complicated. Well, I hope that this presentation has given you a sense for how the center of mass can be used to represent a more complicated system, and that we can imagine and treat the center of mass of a system as a point particle of whose mass is the total mass of the system. We've seen that it can simplify how to talk about dynamics of a more complicated system, and this is a concept that we'll make use of later in this course as well. So that's it for now, but until next time, take care and be well.